So to write the Lewis symbol for any kind of molecule, these are the sort of set of rules that I would recommend going through. So step number one is always count the number of valence electrons in the structure. Okay. So just remember, if it is a polyatomic ion, if it's an anion, you're going to add electrons for the charge because each negative charge is adding an electron. If it's a polyatomic cation, you're going to subtract valence electrons for each unit of charge. Okay. If I could spell, because remember, cations have lost electrons, okay? So that is always going to be your first step, okay? How do you know how many valence electrons you should have? Remember that Lewis symbols are basically your NS-NP configuration, because remember, S can go up to 2, and P can go up to 6 electrons in one of those subshells, and 2 plus 6 is 8, which gives you your octet. So we're just ignoring the D block and stuff, and we're mostly looking at S and P block, okay? So if you're in group 1, that means you've only got 1 valence electron because you've got an NS1 configuration. If you're in group 2, that means you've got 2 valence electrons in your Lewis symbol because you've got an NS2 configuration. Skip the bit in the middle, who cares? Right, Lewis structures only really work well when we're talking about valence electrons in the S or P subshell. So skip over to group 13. It's going to have 3 valence electrons in its Lewis symbol because it has an NS2 NP1 configuration. Group 14 is going to have 4 valence electrons because it's NS2 NP2. Group 15 is going to have 5 valence electrons in its Lewis symbol because it'll be NS2 NP3 configuration. Group 16 will have 6 valence electrons. It'll be NS2 NP4 configuration. Group 17 will have 7 valence electrons, NS2 NP5 configuration, and then finally group 18 in the noble gases has 8 electrons in its Lewis symbol. It is full, thank you, with an NS2 NP6 configuration. 2 plus 6 gives you 8. It's already got an octet. Thank you. All right, so when we count our valence electrons, that is for every atom in the molecule or polyatomic ion, account for charge. Then the next thing is you're going to just kind of lay out how they are arranged in 3-dimensional space. So you're going to pick a central atom. Central will usually have the highest bonding capacity. Okay, so it's going to want to make the most number of bonds. Okay, so if you compare like carbon as a central atom versus hydrogen, carbon has got 4 valence electrons. It wants to get to an octet, which means it's got 4 spaces where it can form a bond by sharing electrons. Whereas hydrogen and helium, remember, they only get the duet because they can only get up to a 1s2 configuration max. Okay. So hydrogen already has 1 valence electron and it wants to get 1 more. So the bonding capacity of hydrogen is 1. It's only ever going to want to form that single bond, okay? So look at the elements you've got and work out what's got the highest bonding capacity, put it in the middle, join everything else to it with single bonds. So join, I'm going to say peripheral atoms for the ones around the outside because I can't think of a simpler word than that right now. Around the outside, peripheral, I don't know, to the central with single bond only, okay? And then what you want to do is you're going to complete the octets on your peripheral atoms, okay? So this is going to be your first approximation, if you like. And then what you're going to do is you're going to have a quick count up of your valence electrons and see if they match what you wanted in step 1. Okay, so count valence electrons. If there's not enough, you can add lone pairs to the central atom at this point. If there's too many, well, delete some, okay? Too many, delete, delete, delete. Okay, so then step 4 is where you're going to check one last thing, is does the central have an octet or not? If it's yes, you're done, son. If it's no, well, you cannot add or subtract any valence electrons at this point because if you did step 3 right, you should have the correct number of valence electrons. So what you're going to have to do is you're going to have to convert lone pairs of electrons on peripheral atoms. There's that word again because I can't think of something simpler. I know someone's probably going to comment and say, just use this easy word. I just know I'm going to spell it wrong. So convert the lone pairs to bonding pairs. Why? Because a bonding pair will be shared with the central atom and will contribute to its octet, whereas if it's just sitting on its onesies on one of the peripheral atoms, it's not helping that central atom. So you do that to get a double bond or a triple bond. That is how they are formed when we run out of valence electrons, but we still need to complete the octet at the central atom. Okay, so let's look at this particular structure then. So we're asked for the dinitride ion. So that's two nitrogen atoms bonded together, and then it is gained as a molecule 2 electrons to form a polyatomic ion, right? So with a -2 charge. So our number of valence electrons then, let's change color just so we can be clear. Our number of valence electrons is going to be, for each nitrogen is in group 15, so we've got 5 valence electrons, so 2 times 5 from each nitrogen. And then we also have to adjust for the charge, okay? So you've gained 2 electrons. You know what? I usually do it like this. So from the nitrogen, we got 2 times valence electrons. From the charge, we've gained 2 electrons, so it's going to be 2 times 1 electron. So that is going to be a total of 10 plus 2, which is going to give me 12 valence electrons. So that is what we are dealing with here. Okay, so then our central atom has to be, well, it doesn't matter which one, but it's going to be a nitrogen. If they were different elements, we'd have to pick, right? So I'm just going to pick left nitrogen as our central because that seems to make sense to me. So I'm going to draw nitrogen, join it up with a single bond to another nitrogen. I'm taking the one on the left as my central because why not? And then I'm going to complete the octet on the other one. 2, 3, 4, 5, 6. One other really important thing you need to do when it's an ion is you actually have to say, ooh, it's an ion. So we're going to use square brackets around the whole thing and then give it a charge to say, hey, this is a 2- ion. Otherwise, it's technically wrong. Okay, so let's have a little count up of our valence electrons and see what we got. So 2, 4, 6 from the lone pairs, plus another 2 from that bonding pair. We've got a total of 8 valence electrons. We're supposed to have 12, so that's no good. So this is where we'd start adding bonding pairs of electrons to our central atom, which in this case is this nitrogen. So I can add 2, 4, like that. So now I should have 12 if I can count properly. Can I count properly? Debatable. Okay, let's see what we got then. So we should have 2, 4, 6, 8, 10, 12. So now we've got 12 valence electrons. Good. Okay. So what about our central atom, which is this guy over here? Does it have an octet? And if we count around it, it's got 2, 4 electrons in lone pairs, and then 6 if you add in that bonding pair. So octet, no. So what we're going to have to do is convert a lone pair on one of the peripheral atoms to a bonding pair. So I'm going to pick this one because symmetry is good, and we are going to move it so it becomes shared. Hopefully this line thing that I'm about to do will work. Right, so we're going to move this from here to here, so it is shared between the 2 nitrogens, okay? So that's important because we cannot increase our number of valence electrons. So I'm going to redraw this nitrogen. Now we have a double bond between, actually that looks kind of ugly, I'm going to draw it in a minute, between the 2 nitrogens, okay? And that's got a 2- charge. Okay, so switch to my drawy thing. So keep it in brackets. Oh, no, I didn't want you to be in that color. That'd be so strange. Right, so we should have nitrogen bonded to the other nitrogen with now a double bond. So remember that double bond is 4 total electrons, if you're keeping up and counting electrons. And then we still have 2 lone pairs on the central nitrogen. And because we've moved one of the lone pairs from the nitrogen on the right to being a bonding pair, we also only have 2 lone pairs of electrons on this nitrogen. So let's just have a little tot up and always double check you think your structure is good. So we have 2, 4, 6, 8, 10, 12 valence electrons. Good. And does our central nitrogen have an octet? Well, it's got 2, 4 electrons in lone pairs, 6, 8 in bonding pairs. So it has got an octet. So we can be pretty happy that this is our correct Lewis structure.